Okay, our next speaker this morning is Anthony from University of Melbourne, talking about real-life contexts in first-year calculus classes. So over to you, Anthony.
Thank you. Hi, I'm Anthony from University of Melbourne. Mathematics isn't just a collection of assorted, unrelated facts. Hopefully, most of us would agree that it's more like a tapestry of interconnected ideas, and the better you understand, or the more of those connections you see, the better you understand the mathematics as a whole. That's kind of recognised in mathematics education. For instance, the National Council of Teachers of Mathematics in the US, back in the 2000s, wrote this in one of their documents, Guidance for Teachers. When students can connect mathematical ideas, their understanding is deeper and more lasting. They can see the mathematical connections and the rich interplay amongst mathematical topics. There you go. Connections in mathematics, certainly there's lots of connections, and the better that students appreciate those connections, the better empowered they are to understand the mathematics and to learn the mathematics. So in the mathematics research literature, there's identified different types of connections. There's, you can think of intra-mathematical connections, connections within mathematics itself, and extra-mathematical connections from bits of mathematics to other disciplines or the real world. Even within the intra-mathematical connections, it's identified a few different types there. I won't go into those, but the last one, the connections between mathematical strands, is the most relevant for today. So these are connections between different areas of mathematics that contribute to the conception of mathematics as an integrated whole. Okay, so with that in mind, that mathematics is a beautifully interconnected, rich interconnected web of things. On the other hand, if you look at a typical first-year mathematics subject, at least the first-year calculus subject that I teach, you often see this, what looks like more like the hodgepodge of unrelated topics. So here is the sections, the topic list from my first-year calculus subject. A bit of some limits, some hyperbolic functions, some complex numbers, some this and that. Not necessarily, doesn't necessarily appear to be a nice unified whole. Understandable why that is, because some of these subjects, they serve different stakeholders. It's sort of a bit designed by committee. You have to cover vectors for the physicists, and you have to cover differential equations for the engineers, and this and that and this and that. And so you end up with a subject that looks like this. Of course, expert mathematicians recognise that there are connections between these things, but do the students see those? Maybe not so much. So in an attempt to address this a little bit, in an attempt to help students see the subject as a bit more of a coherent whole, we tried an innovation, which was introducing an embedded real-world context into the subject. So the key idea here is that we start the semester with a single real-world context, that we maybe introduce it in lectures at the start of the semester, say a little bit about it. I'll give some examples of those in a moment. And then over the semester, every time we introduce a new topic, we link that back to the context one way or another, maybe through an assignment, maybe through tutorial exercises, maybe in lectures, and then it pops up again on the final exam. Some examples of the contexts that we used. These was the first one. So here's an example of the lecture slide that we showed in the first lecture, just showing some of the different ways that mathematics can be applied to bees. So from this honeycomb conjecture here, which was a theorem, proved that hexagonal packings are, in a sense, the most efficient way of filling space. So the bees basically have found the most efficient way to use their wax to build their hives. There are some bees. There's a native Australian bee species that builds nests that look like that. And of course, you can use things like calculus to model bee populations. So this was also very topical because at the time there was an outbreak of a bee parasite which started in Newcastle and has since spread around other parts of Australia, this varroa mite. So that was in the news, and so it was very topical at the time. So just some examples of how we link this in with the different topics. Here, for instance, is In lectures, we used B hexagons, B honeycomb to help illustrate the difference between sequences and series. So you have a sequence of the number of cells in a particular ring, and then the partial sums of a series is what you get if you add those up. So here are some examples of questions that we used in tutorials or assignments. So some calculus, basically use an integral to find the volume of this catenary shaped beehive. Here is a population model, a logistic population model of a bee species. And so we managed to link every topic in the subject back to this context in various different ways. So, okay. So that was one. Another one we did was rivers. There's a picture of the Yarra River, the river through Melbourne, just upstream of Melbourne a little bit. So this was quite topical too, because the summer before this unit was taught, there was a lot of floods. There was floods in the Murray River system. There was floods in the Maribyrnong River in Melbourne. So, rivers had been, again, quite topical. So here's some examples of how we link this in. Some fractal geometry of rivers. If you look at the number of branches, you get this approximately a geometric sequence, the number of tributaries of particular orders. And of course, if you add those up, you get a geometric series. So here is an excerpt from the original publication about that from the 60s or 70s, or from the 80s. Cool. So that was something from lectures. Here was an example of an assignment question, biological control of carp. Carp is an invasive fish species that has is a problem in many Australian waterways, and particularly during floods. It spreads a lot during floods. So again, that was there was talk again about, well, it's been a biological control mechanism for carp's been discussed in Australia for quite a while now, and the idea being to release a virus that will spread through the carp and control the carp. And I mean, don't want to discuss the pros and cons of that, but still, there's some nice mathematical modelling there. So here was an assignment question based on an infectious disease model, an SI model applied to carp. Now, this model here, of course, is a little bit simplified. A real model, people really do use compartment epidemiological models in modelling carp. They use something a little bit more sophisticated than an SI model, but the real models aren't accessible to a first-year calculus student. So this is sort of typical of the way we link these things in, using authentic ideas, but in a simplified way that makes them accessible to the students and with nice, easy numbers rather than realistic numbers, because on the final exam, they have to do the final exam without access to technology. So taking the real authentic ideas, but simplifying them down to make them in a way that's accessible to first-year students. Cool. Another one we did was space. This was right about the time of the James Webb Space Telescope had come online, and so there was a lot of nice, beautiful photos of the universe appearing in the media. So here's an example of an integration question in the context of space, a satellite orbiting through the Van Allen belts, and so it has some periodic radiation exposure, and so an integral there to model that. Cool. Okay, so that was one. There was that intervention, but so this was hopefully our hypothesis was that hopefully this sort of linking every topic back to the real world context might help students. Well, one, help motivate the subject, help engage students a little bit. It was fun for the lecturers too, but also, does that have any flow-on effects to those intra-mathematical connections? Does it help the students appreciate particularly these connections between different mathematical strands? So we also did some research to try to investigate that. So our research questions were, well, firstly, does the intervention have any difference? But before we can kind of answer that, what's the baseline? So what mathematical connections do students bring into the subject when they're arriving at the university, when they're arriving at our subject? What's the baseline there of the mathematical connections that they see between the topics and the subject? How do those beliefs change over the course of the subject? And then finally, does the intervention make any difference? Okay. So which mathematical topics of first-year calculus do students believe are related when they commence the unit? How do the strength and nature of those beliefs change over the semester? And does their real-world context make any difference? So the context, the subject it's a large first-year mathematics subject with between 900 to 1,400 students in a semester, and then also runs in summer semester in intensive mode with a smaller intake. The prerequisite is VCE specialist mathematics, or an equivalent university subject. So these are students who've already done the equivalent of like 2 semesters worth of calculus and pre-calculus, trigonometry, integration, differentiation. And so you've already seen the subject, the topic list, differential equations, hyperbolic functions, complex exponentials, and so on. So it's not so much an introductory calculus subject as building on a reasonable background of calculus knowledge already. Mostly science, commerce students, but a few from other disciplines, and mostly not maths majors because the students specialising in maths typically take typically take an advanced version. Otherwise, fairly standard delivery of 3 lectures and a tutorial each week, and weekly assignments and an exam. Okay, so the study design was we did pre and post surveys. So survey at the start of semester, survey again at the end of semester. We did it in 2 semesters without the case study intervention, so just the standard delivery of the subject, and we did it in 3 semesters with the intervention. Most of them normal semesters, a couple of them summer intensive semesters. The survey questions, there was a few other questions, but I'll just focus on the ones that are relevant to this. For each pair of mathematical topics below, state whether you believe the topics are related, not related, or unsure. And if you said related, optionally give a comment, an explanation why. So there was the list of pairs. So we chose the pairs that kind of captured the key concepts from the subject, but also ones that are familiar to students, ones where they'd have enough familiarity with the topic that they know what the words mean. So we're not going to put on there something that we expect to be brand new to the students, but things that we expect they'll have some familiarity with. So integration, complex numbers, differential equations, exponential functions. And so it's those 4, and it's the full set of combinations of those 4. Okay, so what are the results? Oh, well, here's the figures. So there's the enrolments in the column here, so there's the total enrolment in the subject. This is the number of students who did the pre, this is the number of students who did the post, and this is the number of students who did both. So, not huge response rates in the single figures percentages, but still that's how it is. Cool. So results. So a bit of information on these slides, but putting it all in the one spot so we can get through it all. All right, so what do we see here? So this was, do you think that integration and complex numbers are connected, are related, agree, disagree? So in this one is the pre-semester in the semesters when we didn't do the intervention. The green one, so the blue is the semesters without the intervention. The green is the semesters with the intervention. So this is the pre-semester in the semesters when we did have the case, the real world context intervention. And so pre-semester, pre-semester, pre-semester. So in this one here, we see that, for instance, 49% of students thought that integration and complex numbers were not related when they came into the subject at the start of semester in the semesters without the case study, and a similar percentage, 40.5%, in the semesters with the case study. Cool. And then these other ones here is the post-semester. So in this case, we see that at the end of semester, 90% of students agreed that integration and complex numbers were related by the end of semester. And then a few here that are unsure. Okay, so cool. So interestingly, a big chunk of the students here, about 40-something%, positively believe when they start the semester that integration and complex numbers are not related. So, I mean, they had an option of unsure. So, they could have chosen, I'm not sure. They had the option of choosing unsure, but they've chosen the epistemologically stronger position here of, I believe they're not related, but drops down to much smaller levels by the end of semester. So that's the fact that it's much higher here is not that surprising, because we explicitly cover using the complex exponential to do integration, integrals of e to the something x cos something x, or e to the something x sine something x using the complex exponential. So the fact that it increases is not that surprising, but still the fact that it's so high at the start of semester was a bit surprising. Okay, cool. So that's integration and complex numbers. Similar picture for some of the other topics, complex numbers and differentiation, basically the same picture. Complex numbers and exponentials, basically the same picture. A little bit higher agreement here because maybe some students have heard of complex exponentials before. Cool, so that's the ones involving complex numbers. However, very different picture when we look at the ones that involve that don't involve complex numbers. So differential equations and exponentials, basically everyone already agrees at the start of semester that they're related, and it stays that way over the semester. Same with integration and exponential functions, and same with integration and differential equations. So putting all those together on the one picture here, you kind of clearly see there's two different kind of groups here. The ones with the complex numbers, generally students didn't see. Well, let's call these the calculus topics: integration, differential equations, exponential functions, because they're typically kind of taught in the calculus part of the course. Students already see the calculus-y topics being related, but they don't, much less so, see the complex numbers topics related. So complex numbers is more of an algebra topic, so they come into the subject with much lower levels of appreciating the connections between the algebra and the complex, the algebra and the calculus topics. Yeah, and interestingly, quite high agreement here, quite high agreement that they're not related. So, which does change over the course of the semester. Cool. So, in summary here, what's our interpretation? Most students already saw the calculus topics as connected, so they're coming into school already seeing those connections. So that's great. Sounds like school curricula are helping students make those connections between the calculus topics. So good news. I'm happy B. On the other hand, a lot of students didn't see the complex numbers as connected to the calculus topics. In fact, a lot positively believe they weren't connected. So are the school curricula, could the school curricula be contributing to this? Like for instance, if you look at the VCE, the Victorian Syllabus Study Design, it separates out the topics into different study areas. There's I forget the exact terminology now, but there's like a calculus and functions section, which includes the differentiation, the exponentials, and then there's an algebra section, which includes the complex numbers. So the way these sort of topics are delineated, could that possibly be contributing? Maybe students are used to, we're doing the algebra module now, we do the complex numbers, now we're doing the calculus module, and we do the other topics. Perhaps. But fortunately, it changed over the semester, so we got happy B again. Certainly by the end of semester, the students are seeing connections between those topics much more strongly. Okay, so that addresses those first two questions. What beliefs do those students come into the subject with? How do they change over the course of the semester? What about the impact of the intervention? Well, looking at these figures, not really seeing any difference there, not really seeing any signal there in terms of the difference between the blue and the green. Sure enough, none of those differences between the semesters with or without the intervention were statistically significant. So, is it sad to get a negative result? Not necessarily. So, yeah, right. Cool. So that's, however, we also have the qualitative data. Remember, the question said, if you answered that they were related, explain why. So we have some text responses there. So we analysed those. We limited to the respondents who completed both the pre and the post surveys so we could see any changes, and students who gave at least one comment. So that was 80 students in total. We compared the pre and the post semester comments, and we coded them as either pre-semester comments were better, post-semester comments were a bit better, or a lot better, or they were similar, or not useful. So better meaning we didn't try to pin that down exactly, but that would typically be like a more detailed comment or a more insightful or whatever. And then we counted the numbers of topic pairs that showed improved understanding of the connections. So what did we see? We found that the responses tended to be general or vague before the semester, but generally became a lot more specific and more confident after the semester. So here was one example. The same student on the pre-semester survey wrote, differential equations that involve exponential functions exist. Okay, so that was a student who agreed that differential equations and exponentials were related, but their example is a bit pretty vague, whereas in their post-semester, their answer was use of exponential expression as the substitute for y when solving second-order differential equations. Great. You're solving a second order differential equation. What do? You start with y equals e to the homogeneous. You start with y equals e to the lambda x. You substitute it in, you get your characteristic equation, you solve for lambda. So a much more specific example there, and that was quite typical. So the qualitative results showed an improved quality of the understanding of those connections. So that's not really seen in the, you don't really see that here because the students are agreeing, but actually the nature of that agreement, the nature of that appreciation has improved. And we'll more confident as well. So we'd see questions like, oh, I think that this, I think they might be related, or oh yeah, they're related. IDK, I don't know. Whereas the post semester would be much more confident as well. Cool. So to further delve into, does the sorry, the cameras, the audience is not really seeing me there. Is that a bit better? There we go. Hi everyone on Zoom. To further delve into the impact of the intervention, we looked at so comparing the pre and the post comments. How many different topic areas? Remember, there was the 6 different pairings of these 6 different pairings here. How many of these different pairings did we see an improved quality of answer? So here we go. So here we start to see a little bit of a signal, perhaps, for the impact of the real world context. So we have, so how many students gained an in-depth understanding of links between all 6 topics? So for all 6 topics, they gave a better quality answer in their written comment in the post versus the pre. Well, there was 11 in the semester with the real world context, and there was 7 in the semesters without the real world context. And so the distribution here is a bit more top heavy, whereas you got more at the lower level here. So we're starting to see some signal there in that qualitative data that maybe the real world intervention has helped students recognize those connections between a wider range of topics. So we also looked at there was one other analysis which I won't show here, but it's in the paper if anyone's interested. So we are starting to see some evidence that the real world context helps students recognize connections between more topics. Of course, the real world context intervention has other benefits. Got nice comments in the student feedback, helps improve engagement and so on. Not covering that here, but starting to see perhaps some evidence that it does have some impact there from the qualitative results. Cool. So the kind of takeaways here is particularly this this picture here of that positive 40-something% of students positively believing that complex numbers and integration, complex numbers and the other calculus topics are not connected. That's kind of surprising. That really says to me that students are coming out of school positively believing that they're not connected. Not just, I'm not sure, but they positively believe that those topics aren't connected. So if we want students to develop those connections, perhaps worthy of some further investigation there to see how is the structure of school syllabuses contributing to this? How could it? Are there any changes we could make there to help smooth that out? But fortunately, particularly in a subject where we explicitly include links between complex numbers and calculus, we see that doesn't persist. All right, a couple of other little observations which I won't go over now, but they're in the paper if anyone's just interested. All right, thanks.
Thanks, Anthony. Have you presented these findings to teachers in Victoria, either at the Mathematical Association of Victoria annual conference, which is sort of next week every year? It's a massive conference. I guess, do you see this as an issue that they're not seeing the connection between complex numbers? And have you done something about it in terms of talking to the teachers?
Yeah, good question. No, I haven't done anything about it yet. But that's the MAV conference would be a good forum for that, for instance. Yeah. Thanks.
Questions for Anthony? Neve?
Hello, thank you. I thought that was really, really interesting. I really enjoyed hearing about that. Did you get any feedback from the students as to whether they enjoyed working with the problems more because they were in context? So rather than just seeing the connections, but just like, did they prefer it? Did they find it more interesting? Were they more engaged with it?
There was a few comments on the end of semester survey, the standard university end of semester survey about it. So there was no negative comments about it. There was a few positive comments about it. So we didn't like run a separate survey specifically about that because you don't want to overload students with everything. But I think that it was positive for the student experience. Sure, it is a bit of work to produce these, to come up with these case studies. So I wouldn't try to keep producing new ones every semester. But once you have the bank of questions and applications, they can be reused reasonably easily. Yeah, I think the students. I think it was a positive for the students for their engagement. Yeah.
Okay, I have a question now.
Ash has got a question online.
Yeah.
Question online, yeah.
Sorry.
This one here in the chat.
Yep.
It's really interesting to see how you connect calculus and real-world context, in particular things that you can find in nature. When you use these models, do you first introduce the real-life application and then move to the maths behind it, or the other way around? So I suppose we first introduced the real-life application in lectures in like week 1 with some of those slides like I showed, where we just sort of discussed the context without delving into any specific applications at that stage. It's more the context and its general relationship to mathematics, like this kind of thing here, and then link it into the local context as well. So, for instance, if there's some connection to what's happening in Australia or in Victoria or in the students' lives, and then when we introduce a new topic, we kind of link it back in. So I suppose the answer is we introduce the context first at the start, and then over the semester each time, at some point, whether it's on an assignment or on a tutorial in a lecture, we link it back to the current topic. We don't necessarily like go into huge amounts of detail of the derivation of the models, for instance. Like in this example here, we talk about population models in lectures, not specifically of CARP or not specifically of these, but students have seen the concept of population models before they see it, before then it gets applied to the context in tutorial or assessment. Was there any other questions on the chat there?
Thanks, Anthony.
Thanks.